Look around you. You live on a highly structured rocky planet, orbiting a stable star, surrounded by complex biological life. But if you rewind to clock 13.8 billion years, every piece of that structure disappears into an absolute featureless black void. And then, raw energy violently floods the empty space. That initial burst, the Big Bang, did not instantly assemble planets, stars, or human beings. It produced nothing but a hyper-expanding, chaotic soup of heat and subatomic particles. Which leaves us with a mechanical problem. By what physical mechanism does a featureless, chaotic explosion organize itself into the highly complex reality we experience today? The answer requires looking past isolated historical events. To understand our origins, we have to trace a single, uninterrupted 13.8 billion-year chain reaction of cause and effect. The assembly of our universe began in fractions of a second. Within milliseconds of the Big Bang, the expanding energy cooled exactly enough for the first subatomic particles, like quarks and photons, to physically emerge. By the 2-minute mark, the temperature dropped further, allowing protons and neutrons to bind together. This brief window forged the very first elements in existence: hydrogen, helium, and trace amounts of deuterium. This graph maps that initial chaotic expansion. Over 400 million years, the extreme exponential growth curve flattens, leaving massive primordial clouds of hydrogen and helium. Then, gravity took over, continuously pulling these gas clouds inward, aggressively compressing them and driving up their internal density. As the gas compacted, the friction generated immense heat. When the center of these clouds crossed a threshold of 10 million degrees Kelvin, the hydrogen atoms began smashing together to form helium. Nuclear fusion ignited, and the very first stars lit up the darkness. Gravity took the scattered gases and crushed them into massive light engines. The underlying physics of the cosmos drove the raw materials to assemble themselves. These early stars, ranging from massive blue giants to tiny red dwarfs, did not drift alone. Their immense mass drove them to cluster together, forming the deep space predecessors to modern galaxies like our Milky Way and Andromeda. This 3D wireframe model illustrates exactly how that clustering was possible. Dark matter acts as an invisible architectural scaffolding. It doesn't emit or absorb light, but it exerts an enormous gravitational pull, acting as the structural grid that anchors scattered stars into tightly packed galaxies. As the universe continued to expand, these early galaxies gravitated toward one another. They clustered along the dark matter web, forming the largest contiguous gravitational structures we know of today. Within those early clusters, massive blue giants burned through their nuclear fuel. When fusion stopped, their cores collapsed, triggering violently brilliant supernova explosions. Those turbulent shockwaves were highly productive. The extreme heat and pressure of a dying star forged the physical elements required to build dense, rocky matter. Billions of years later, in one specific galactic neighborhood, a new star, our Sun, ignited. It was entirely surrounded by the swirling heavy elements and dust left behind by those ancient supernovas. Trapped in the Sun's orbit, these heavy particles slammed into each other. Dust grains fused into pebbles, pebbles into boulders, and boulders accumulated into planetesimals, the rough, molten prototypes of our rocky planets. One of those growing planetesimals was the early Earth. Its development was defined by extreme kinetic impact. A Mars-sized object named Theia collided directly with our young planet, fracturing the crust and launching molten debris into orbit to form our moon. The impacts continued during an era known as the Late Heavy Bombardment. Massive stray asteroids continuously battered Mercury, Venus, Mars, and Earth, cratering their surfaces and delivering crucial chemical compounds. Habitability actually required this extreme physical violence. The continuous physical battering settled the rocky planets into their final forms, laying the chemical foundation required to support liquid water and complex molecules. Down in the microscopic chemical pools of the early Earth, the physical chain reaction transitioned into biology. Simple, single-celled organisms called prokaryotes emerged from the heavy elements. These primitive organisms operated as biological engines. They steadily excreted oxygen, gradually transforming the planet's toxic atmosphere and generating the high-altitude ozone layer that shielded the surface from cosmic radiation. That breathable, shielded atmosphere acted as a biological accelerator. Life grew in complexity, pushing upward from simple microbes to early vertebrates, spreading across the shifting supercontinent of Pangaea, surviving mass extinctions and driving the rise of dinosaurs and, eventually, mammals. Biological evolution took the raw, heavy chemistry of a battered rock and reorganized it into interconnected living ecosystems. We study this timeline as if we are external observers, but humanity is the direct physical culmination of it. The iron flowing through your blood right now was forged in the explosive death of massive early stars. The oxygen you are breathing was manufactured by microscopic biological engines billions of years before you were born. Human consciousness is simply the universe reaching a state of extreme organization. It is raw matter that has finally assembled a system complex enough to open its eyes, look back into the cosmos, and understand its own creation. As we map the future, navigating a shifting climate, engineering futuristic technologies, and launching spacecraft toward other worlds, we are actively writing the next chapter of an unbroken 13.8 billion-year chain reaction.